Welcome to the ultimate guide on building a working solar water heater using nothing but reclaimed materials, and we'll prove how well it works. But first, here is the final system in action, demonstrating how we can harness solar power from literally trash. Look closely. Steam is rising, the thermometer shows significant heat increase, and this entire can collector is piping hot. This hot water came from sunlight and trash. No electricity, no gas, just thermodynamics doing its work. It's a surprisingly effective way to save energy. Now, let's talk about why this is even important. Why hot water is an energy problem that sunlight can solve. Water heating is often one of the biggest household energy costs. Every time you turn on that hot tap, you're running up a big bill. Even when considering solar systems, they are often prohibitively expensive, especially in rural or off-grid areas where people need them most. So I asked a simple yet ambitious question. Can I build a working solar water heater from discarded materials, making it truly accessible to anyone, anywhere? To understand how this simple system works, we need to cover the core science. It's simple, but powerful. First, sunlight is pure energy, delivered as radiation. Our goal is to capture as much of that incoming energy as possible. This is where black surfaces come in. They absorb far more heat than light ones. And metal, like aluminum cans, transfers that heat quickly and efficiently to the water inside. Water itself has a high specific heat capacity, meaning it's excellent at storing the thermal energy we transfer to it. Remember this, we're not creating energy. We're simply capturing and concentrating the immense energy the sun already sends us. With the science understood, let's look at the simple three-part system we are building. The whole setup consists of a solar collector, where the heat is absorbed, a water flow system, and a storage tank. Our solar collector is the stack of painted aluminum cans, acting as the heat absorber, linked to the tubing for water circulation and heat transfer. It's time to gather the materials. The best part? Everything is essentially free or found. Our main components are collected aluminum cans, used plastic bottles for the insulation, and some scrap wood to build the frame. You'll also need some simple tubing for the water flow, and crucially, a can of black, heat-resistant paint to maximize absorption. That's the concept and the materials. Now let's get our hands dirty and build it step by step. Welcome back. In this second part of our DIY solar heater project, we are diving into the core construction using our collected scrap materials. If you missed part 1, we gathered our scrap. Now we're building the functional components to transform simple sunlight into useful heat. Remember, the goal is a low-cost, effective solar water heater. We'll be focusing on optimizing heat capture and minimizing loss throughout the build. We'll be tackling the frame, prepping the absorber, setting up the water path, and finally, insulating and positioning the unit. First up is the frame. Use your scrap wood or cardboard to cut the pieces and assemble a rigid structure. Crucially, build in an angle for optimal sun exposure. The angle matters because sunlight is directional. Positioning your collector perpendicular to the sun's rays for the longest duration maximizes the energy harvest. Next, let's prepare the heart of the heater, the heat absorber. This component needs to capture as much solar radiation as possible. Clean your cans or metal sheets thoroughly, and then paint them entirely black. This step is non-negotiable for efficiency. Black increases absorption efficiency by reducing reflection. Dark, matte surfaces are the best conductors for converting light energy into thermal energy. Now stack your prepared cans or tubes tightly into columns within the frame. Ensure they fit snugly, forming a continuous path or network. The goal here is maximum surface contact for heat transfer. We need the water flowing through to touch as much of that hot black surface as possible. Next, insert your tubing or bottle connections at the inlet and outlet of the absorber array. Use sealant to ensure the system is completely watertight and leak-proof. The design of the water path ensures water stays in thermal contact long enough to heat up significantly as it travels through the collector. Apply a layer of insulation using cardboard, plastic wrapping, or newspaper around the back and sides of the frame to reduce heat loss points. Heat loss is the enemy of efficiency. The better insulated your collector is, the higher the temperature the water will achieve. With the components in place and sealed, secure the unit. Position it outside, making sure it faces the sun according to the angled frame you built. We now rely on one thing, solar radiation density over time. The heater will start working immediately, absorbing energy from the sun. The build is complete. Now for the exciting part. Let's test it. Welcome back to part 3 of our DIY solar water heater project. Today, we're diving into the results and the physics behind its performance. We've built it. Now it's time to test if this simple system can effectively convert sunlight into usable heat. The goal of this test is straightforward. Measure the temperature difference between the water entering the system and the water exiting it after sun exposure. Before we start heating, we need a baseline. This gives us the point of comparison needed to accurately measure the system's efficiency. Here is our initial cold water temperature reading, taken directly from the source before entering the collector. This starting measurement is critical. This is our control point, against which all our performance gains will be measured. Now, let's put the collector to work. We've introduced the water flow and started the test under direct sunlight. You can see the water flowing through the internal channels, exposed directly to the sun's radiation, and the timer is running, tracking the exposure duration. As the black surface absorbs solar radiation, that energy is transferred to the water flowing inside. This is real-time thermal transfer. The test is complete. Let's analyze the data and understand the simple physics governing our solar water heater's performance. Comparing the inlet and outlet temperatures, we see a clear and measurable increase. This difference represents the total thermal energy gain. The primary factors driving this heat gain are the duration of sun exposure, or time dependence, and the intensity of the direct sunlight. It's simple science. More exposure time and higher sunlight intensity equals more thermal energy absorbed by the system. While the results are positive, it's important to discuss the limitations of this basic design to maintain credibility. Factors like cloudy weather significantly reduce efficiency, heat loss occurs rapidly without insulation, and the speed of the water flow directly impacts how hot the water gets. Engineering is all about iteration. Based on these results, we can already identify several key upgrades for a version 2.0. Key upgrades include adding a glass cover to create a greenhouse effect, using coiled copper tubing for better heat exchange, and a reflective backing to maximize solar absorption. Remember, this is version 1. It proves the concept. The process of engineering is continuous iteration, learning from the first attempt to build a better system. We've gone from raw materials to a functional device, proven through testing and understood through physics. Here is our completed solar water heater, demonstrating the potential of simple, accessible technology. This project wasn't about building a gadget. It was about proving something simple. Energy systems don't have to be expensive, just intelligent. If you enjoyed this project and want to see more DIY energy solutions, please like this video, share it with others, and subscribe to our channel for all future updates.